Let's construct a Lagrangian for two coupled and driven anharmonic oscillators. The system I'm going to analyze in this video is an electrical system, but I'm going to be making a lot of analogies to mechanical systems throughout this video. So let's have a look at the system of interest. This is a circuit diagram that describes the system. I'm using the lumped element model. Now that is a way to simplify descriptions of electrical circuits. In reality, these electrical systems are three-dimensional and they consist of chunks of material. And the material is made up of many atoms. But what we're doing is we're ignoring many degrees of freedom. And we're simplifying the system into a discrete topology. And that discrete topology consists of circuit elements. And circuit elements include capacitors, inductors, and the very special superconducting device, which is the Josephson junction. So this is the symbol for a Josephson junction. And the Josephson junction is a very important component in the transmon. And the transmon is used to create superconducting qubits in the field of quantum computing. So this over here can be thought of as one oscillator. It is an anharmonic oscillator. That means it's not harmonic. The energy levels are not evenly spaced when we translate this description into quantum mechanics. So here we have an anharmonic oscillator, and here we have another anharmonic oscillator. We can call this oscillator 1 and oscillator 2. Between these two oscillators, we have coupling. And I've put capacitive coupling and inductive coupling. So we have the capacitance between 1 and 2 and the inductance between 1 and 2. So if we just took this section of the system, what we would have is an LC oscillator. So when you have a capacitor and an inductor, that is a harmonic oscillator. It's an LC oscillator. But if you exchange this inductor for a Josephson junction, then that introduces a non-linearity. And that is where anharmonicity comes from. So instead of having evenly spaced energy levels, when we quantize the system, we're going to have slightly different spacings between the energy levels. And that's exactly what we want when we can make the two-level approximation. And that is the qubit approximation. That allows us to make qubits out of oscillators. So we've had a look at the overview of what's going on in this. We're just using the lumped element model to model this electrical system. And we've talked about coupling between the two oscillators. There is also external driving. We have a driving voltage, which is capacitively coupled to this first oscillator. And the second oscillator also has an external voltage, which is capacitively coupled to it. And this symbol over here just means that it's grounded. So we're grounding the circuit at these locations over here. Now, when we have this lumped element model description, it's very useful to identify nodes. So we have a circuit node over here and a circuit node over here. And what we're going to do is we're going to look at those nodes and we're going to assign coordinates to those nodes. If this was a mechanical system, positions of particles or angles, they would be our coordinates. Right? For a pendulum, the angle is a coordinate. And for a mass on a spring, we look at the position as a coordinate. But there's no position in angles over here. This is an electrical system, not a mechanical system. So what we can use is the flux. So this capital phi over here is the flux. So we have the flux at this first oscillator and the flux at this second oscillator. That is what we're going to use as our coordinate. And the mathematical description is very similar to the mechanical analog. But instead of these position variables and these angle variables, what we're going to be using is flux. This is an electrical quantity. And instead of velocity, what we're going to be using is phi dot, the time derivative of the flux. And that is analogous to velocity for mechanical systems. So now, what I want to do is I want to just quickly go over all of the quantities I've defined over here. So these are the coupling parameters. We have the coupling capacitance between oscillators 1 and 2, the coupling inductance between oscillators 1 and 2, and then we have the energy associated with this Josephson junction 1 and a capacitance associated with the Josephson junction. And we have an analogous setup over here we have the capacitance of Josephson junction 2 and the energy associated with Josephson junction 2. And these sources of voltage, these external driving voltages, they are coupled capacitively with a capacitance labeled CV1, and over here we have CV2. These voltages are in general time dependent. So I've explicitly stated that this is a function of time and this is a function of time. We can model these external voltages as cosinusoidal functions. Or we could even multiply that cosinusoidal function by a Gaussian envelope. So we can imagine a pulse of a wave coming in through. So like a little wave packet of voltage that we're sending in over here, and a wave packet of voltage that we're sending in over here. I have also defined the sum of these three capacitances and these three capacitances in this condensed notation. So we have C1 and C2. So if we have a look at C1, C1 takes this capacitance, and this capacitance, and groups it into one quantity. And C2 takes this capacitance, and this capacitance, and groups it into one quantity. That's going to be very useful when we write down the kinetic energy later in this video. So now that we've defined quantities, let's go ahead and construct the Lagrangian. So the Lagrangian in mechanical systems is the kinetic energy minus the potential energy. But we don't have positions and velocities over here. Instead, we have flux and time derivatives of the flux. And we have two coordinates that we're dealing with over here. And these coordinates are associated with each of the anharmonic oscillators. So the Lagrangian depends on the two coordinates, phi1 and phi2, and it also depends on the velocities, or the time derivatives of the coordinates. So that's phi1 dot and phi2 dot. And I've also put in an explicit dependence on time. Now that explicit dependence of time comes from these external voltages. There is also an implicit time dependence in all of these quantities over here. So these are dynamical quantities and they change with respect to time. But what we've got over here is an explicit time dependence as well as implicit time dependences. And this Lagrangian can be separated into two sections, so two terms, or two collections of terms. We have the kinetic energy, which depends on the velocities, or the phi dots, and time over here. And then we have the potential energy, which in this case just depends on the coordinates. So we're taking all the dependence on the coordinates, we're putting that into one part, and we're taking all the dependence on the velocities, and we're putting that into one part. So let's start off by writing down the potential energy. Or another way to think of this is the inductive energy. What are the contributions to the inductive energy over here? So I'll write down some of the contributions. So first what we want to do is we want to take care of this Josephson junction. So we have two Josephson junctions over here, and they both contribute inductive energies. And the form of this inductive energy is cosinusoidal. So it has the form minus EJ1 cosine of 2 pi phi 1 over phi sub 0. So this is the inductive energy coming from this oscillator over here. And this is analogous to the potential energy of a pendulum. You can think of this as a pendulum or a rotor. It is the electrical analog of a pendulum, an anharmonic oscillator. And what we have over here is this cosinusoidal dependence. So this is very, very important. This is characteristic of a Josephson junction. And this phi 0 over here, that is the flux quantum. So that's Planck's constant over twice the charge of the electron. And we're just putting that in here as a constant, and that's just going to cancel the units of flux out over here. So this is actually a dimensionless quantity, this thing over here, all of the stuff inside the cosine. And there's an analogous term coming from this oscillator as well. We also have minus EJ2 cosine of, we have in the brackets, we have 2 pi phi 2 all over phi 0. So it's just an analogous term. We just have the other coordinate over here, and we also have this other energy over here. So these are the contributions coming from the Josephson junctions. There is also another contribution to the inductive energy. That is this coupling over here. We have coupling between the two oscillators. And the form of this is quadratic. So what we have is plus 1 on 2L12. So L12 is the inductance between these two oscillators. And then what we want to do is we want to take the difference of the flux between these two nodes. Because this inductance is between these two nodes, we want to have phi 1 over here and phi 2 over here. We want to have the difference. And what we're going to do is we're going to take the difference of phi 1 and phi 2, and then we're going to square it. So we have the difference of the flux squared over twice the inductance. So that is the contribution coming from the coupling over here, and that is inductive coupling. Where would we get other terms? Well, if we had inductive driving, if the driving was coupled inductively, then we would also have driving terms over here. But in this model of the system, I have neglected to include inductive driving. There is just inductive coupling. What we do have is capacitive driving, and that's going to enter the kinetic energy. So that doesn't appear in the potential energy. So this is all of the contributions to the potential energy, or we can also think of it as the inductive energy. Now, let's go ahead and have a look at the kinetic energy. There's a lot more going on in the kinetic energy because we also have those driving terms. So what we have to do is we have to consider all of the capacitors. So let's start off with this capacitor over here, CV1. So CV1 is this coupling capacitor which couples to the external driving voltage, which is associated with the first oscillator, oscillator 1. So that's going to have the form CV1 on 2, and then what we want to do is we want to take the difference of the phi dots. So now, instead of phi, we're going to have phi dots, because the capacitors, they depend on the velocity. They are analogous to the kinetic energy. So over here, we're going to have phi dot associated with this node, and over here, we're going to have V1. And V1, that voltage, is actually a velocity. So we can think of this voltage as a velocity by analogy with mechanical systems. So what we're going to have is phi 1 minus V1. And I will neglect to put the explicit time dependence because I've shown that over here. So just remember that this is a time-dependent function in general. It could be constant in a special case, but what we're going to consider is time-dependent functions that usually have the form of a cosinusoidal function. So we have phi 1 dot, we need to have a dot over here because this is a velocity, minus V1. So the important difference between capacitive elements and inductive elements is that there are no dots over here. We're not taking time derivatives. We're just considering flux as the coordinate. And over here we have phi 1 dot because this is the time derivative. It is like the velocity. And this has the same units as this voltage over here. Now, so that takes care of this capacitance over here. Now let's have a look at this capacitor over here. This is the capacitance coming from the Josephson junction. So the Josephson junction has this dependence, which shows up in the inductive energy, and it also has a capacitive energy. Anytime you're separating charges, that's going to introduce a capacitance. So what we're going to have is CJ1 over 2, and this down here is 0 because we're grounded, so the difference is just going to be phi 1 minus 0, which is just phi 1. And we want to take the time derivative of that, that's a dot, and we want to square that. So that takes care of this capacitance and this capacitance. Now let's have a look at the coupling capacitance. So the coupling capacitance is right in between these two nodes, between node 1 and node 2. So what we're going to have to do is we're going to take the difference of those two nodes. So we're going to have C12 on 2, and then we're going to take phi 1 dot minus phi 2 dot, and we're going to square all of that. So you can see what we're doing is we're taking the difference of those velocities from over here and over here. And when I say velocity, I'm saying that in an analogous way. I'm making an analogy to a mechanical system. But really what this is the time derivative of the flux, the phi dots. So this is the contribution that the coupling capacitor makes, and we just have two capacitors left. Let's take care of this capacitor first. That is analogous to this term. So we're going to have CJ2 on 2, and then we're going to have phi 2 dot squared, just like this term over here. And finally, we're going to have an analogous term to this, which corresponds to this coupling capacitor, which couples to the external voltage being applied to this oscillator, oscillator 2. And that's going to give us CV2 on 2. And then we're going to have phi 2 dot minus V2, and all of that is squared. So what we see is that there are a total of 5 capacitors. 1, 2, 3, 4, 5. And they each contribute a term. You can see that all of these terms are quadratic. They have a quadratic dependence on phi dots. They could be phi dot 1 or phi dot 2. So that depends on which node we're considering. And you can also see an analogous quadratic dependence over here in the inductive term. But the difference is that the inductive term depends on the coordinate and not the velocity. That's why we're calling this the potential energy. Now what I want to do is I want to repackage all of this into a more suggestive form. So first, let's have a look at all of the phi 1 dot squareds and all of the phi 2 dot squareds. Where are they coming from? And let's group them all together into one term. What we see is that if we were to expand all of these ones out, we would see CV1 occurring as a coefficient. We would also see CJ1 occurring as a coefficient, and C12. So we would see the sum of these 3 capacitances occurring as a coefficient of phi 1 dot. And that's exactly the quantity that I have defined over here. So we can also do an analogous reasoning for C2. And what I'm going to do is I'm going to write down those terms. So this is equivalent to, we're going to have C1 on 2 times phi 1 dot squared plus C2 on 2 phi 2 dot squared. So just as a recap, where are these terms coming from? These terms are coming from expanding out these guys and just focusing on phi 1 dot. And we can see that we have the sum of 3 capacitances. That's this capacitance, this capacitance, and this capacitance. And this term is coming from the sum originating from here. We have C12, then we have CJ2, and finally CV2. And those are exactly the terms that appear over here. So in this sum, that gives us C2. So that takes care of C1 and C2. And now what we want to do is we also want to look at mixed terms. So these terms are not mixed. They only depend on phi 1 and only on phi 2. But now let's have a look at those mixed terms. So the first mixed term we can consider is the mixed term that contains both phi 1 dot and phi 2 dot. And that comes from here. So that's going to give us a minus C12 phi 1 dot phi 2 dot. So that is a mixed term. And you can see that when we expand this out, we get a factor of 2, and that cancels with this half. So that's the first mixed term that we need to consider. There are also mixed terms that involve the voltages. So over here, we're going to have a mixed term, and that mixed term is going to look like this. We're going to have CV1, and then we're going to have V1, and that's going to combine with phi 1 dot. And we're also going to have an analogous term that is mixed emerging over here. So we're going to have minus CV2, V2, and then phi 2 dot. And you can see that these terms have the same units, but only one of these coordinates is appearing here. That's because this voltage has the same units as this phi dot. So together, this combination has the same units as the square. So if you have phi 1 dot squared, that has the same units as phi 1 dot times phi 2 dot, and that also has the same units as a voltage times a phi dot. So these are all the mixed terms, and now we also have the quadratic terms that depend on V1 and V2. So we have a contribution coming from here and a contribution coming from here. And I'll write that as 1. We're going to have 1/2 C, and which capacitance are we looking at? We're looking at CV1, CV1, V1 squared, plus CV2, V2 squared. So this term originates from both this term over here where we square this voltage and from this term over here where we square this voltage. So that's CV1, V1 squared plus CV2, V2 squared. And one thing I want you to notice about this term is that there is no phi 1, phi 2, phi 1 dot, or phi 2 dot. So the coordinates and the velocities, they don't appear in this term. And when we use this to define the Lagrangian, we're only interested in derivatives of the Lagrangian. So constants that don't depend on the coordinates or the velocities, they're not going to be included. We're not going to care about those terms. We now have all the information necessary to construct the Lagrangian. We have all the terms in the kinetic energy and all the terms in the potential energy. When we substitute the potential energy into the Lagrangian, we have to keep track of this minus sign. So this minus sign will flip the signs of all of these terms. So we'll have plus cosine and plus cosine, and this will become a minus sign over here. We can also expand this term into three smaller terms. And those smaller terms are going to depend on phi1 squared, phi2 squared, and we're also going to have a mixed term that has phi1 and phi2. So that is all of the inductive energies, and that contributes to the potential energy. The capacitive energies, they all contribute to the kinetic energy. And we also have mixed terms over here, and this mixed term over here consists of both phi1 dot and phi2 dot. Whereas these mixed terms, they are responsible for describing how this external voltage impacts this oscillator and how this external voltage impacts this oscillator. So we've labeled them as 1 and 2. Suppose we include this term as well. This term is not going to have any physical significance because it is independent of the phi's and the phi dots. If we kept this in the Lagrangian, then when we took the Legendre transform to get to the Hamiltonian, we would just have an additive constant. So this term would just go along for the ride in the Legendre transform. It would remain unchanged. And then when we translate the Hamiltonian into quantum mechanics, what we would just see is an energy offset for all of the energy levels. So all the energy levels would just be offset by this time-dependent function. So it's a time-dependent constant. It's constant with respect to the phi's and the phi dots, but it is not constant with respect to time. That is because V1 and V2, they have an explicit time dependence over here. So it is actually convenient to remove this term and to ignore it because it doesn't actually have any physical significance. All it would do is offset the energy levels. And we're only interested in differences between the energy levels. We don't care about the offset because that is not physically significant. So now that we have all of the terms in the Lagrangian, what we can do is we can start taking derivatives of the Lagrangian. And we can use those derivatives to find the canonically conjugate momenta. And in this case, for this physical system, the canonically conjugate momenta are q's. They are the charges. Because there are two coordinates, there are also two canonically conjugate momenta, q1 and q2. Let's find q1 and q2. q1 is defined as the partial derivative with respect to phi1 dot of the Lagrangian. Analogously, q2 is defined as the partial derivative with respect to phi2 dot of the Lagrangian. Let's have a look at all the terms that contribute to q1 and q2. So first, let's differentiate the Lagrangian with respect to phi1 dot. Now, because these are phi dots, we're not even going to consider the potential energy. So the potential energy has no phi dots, it only has phi's. So we're only looking at the capacitive terms in the kinetic energy. So we're interested in these terms over here. First, let's have a look at this term. Here we see phi1 dot squared. We can use the power rule, and that's going to give us C1 phi1 dot. So that's from this term. Then this mixed term is going to give us minus C1 2, and when we differentiate with respect to phi1 dot, that's going to leave phi2 dot. And finally, there is a contribution from this term, which is just a constant with respect to the phi1s and the phi2 dots. So we have CV1 and then V1. So it's constant with respect to the coordinates and the velocities, but it is not constant with respect to time. This is a time-dependent function. And there are analogous terms that emerge for Q2. For Q2, this term gives us C2 phi2 dot. This term again gives us minus C1 2, but now instead of 2 we have 1 because we're differentiating with respect to phi 2 dot. That's going to give us phi 1 dot. And finally, we look at this term over here, and that gives us minus CV2 and then V2. So all these terms have the same units. And you can see that there is a crisscross over here. We have 2 appearing for Q1, and we also have a 1 appearing in Q2. So these are not independent of each other. Now, why is there a crisscross occurring? It's because of this coupling. There is coupling between these 2 oscillators. This term and this term, they actually account for those interactions. And what's really neat about this form is that we can actually re-express it in a matrix equation. So what I'm going to do is I'm going to take these terms over here, these terms, I'm going to move them to the other side. And I'm going to write this as a column vector. So I'll do that over here. So I'll write this as a column vector. And in this entry over here, this first entry of the column vector, I'm going to have Q1 plus CV1, V1. And then I'm going to have Q2 plus CV2, V2. So this over here, this is my column vector. And I'm going to write that as a matrix product. So you can see where this has come from. I've just taken this Q1 and I've added this term to both sides. I've taken this Q2, I've added this term to both sides. And now what we're going to have on the other side is we're going to have these terms and these terms. And I can write that as a square matrix multiplying another column vector, or a column matrix. So let's do that over here. If I take this matrix that has C1 and C2 on the diagonal, and on the off diagonal I want minus C12 and minus C12. And then what else I want to do is I want to write down this column vector, which consists of entries phi 1 dot and phi 2 dot. And if we perform this matrix multiplication, what we're going to recover is these terms over here, these 4 terms. And isn't that a very nice condensed way to write this? And the reason I'm writing it in this matrix form is because it allows us to easily solve for the velocities. We can express the velocities in terms of the q's, in terms of those momenta. And that is essential when we're doing the Legendre transform. And that's what we're going to see in later videos in the quantum mechanics playlist. I'm going to be using these expressions to perform the Legendre transform, and that's going to give us the Hamiltonian. So the goal of this video was to construct the Lagrangian for this physical system, or this lumped element model of a physical system. Now that we have the Lagrangian, we have all of the information that we need to construct the Hamiltonian. We just have to do the Legendre transform. And when we get the Hamiltonian, we can translate the Hamiltonian into quantum mechanics by elevating a lot of these quantities into operators. So we turn them into operators. The Hamiltonian becomes an operator. The q's, they become operators. And the phi's, they also become operators. So the flux and the charge become operators. And that allows us to have a quantum mechanical description of this circuit, which is going to be a superconducting circuit. So we can utilize the properties of quantum mechanics in this physical system. So in the next video, what we're going to be doing is analyzing this matrix equation and re-expressing these guys in terms of the q's. So in these expressions, we've expressed the momenta in terms of the velocities. But what we want to do is the opposite. We want the velocities expressed in terms of the momenta. And that's going to allow us to do the Legendre transform. And we'll do that by taking the inverse of this matrix. So that is in the next video in the quantum mechanics playlist, which you can find if you click over here.